Welcome to the answer video of the copper tubing question. In this video I will explain you how you could solve the copper tubing exercise. Heat is produced in the tube and we would like to investigate in this question the temperature profile in the tube wall due to this heat production. For a first rough estimation we assume the tube to be a flat plate, as I already made a sketch of. They give the length of the tube that it's 0.5 meters, so half of the tube is 0.25 meter. And then your first question was, which balance will you use to be able to calculate the temperature in the middle of the tube? Now, of course, temperature is all about energy. You only need the energy balance. And the second question was, which law will you use to describe the flux in the part dx if you set up a small balance over a small part dx of the tube? And that's of course Fourier's law, because that has to do with temperature change. For the second question, we assume the middle temperature of the tube to be 20 degrees Celsius. If you now set up the energy balance over a small part of the tube dx, you can investigate the temperature profile in the tube from x is 0 to x is L. Furthermore, you get some information that you need to calculate the temperature at a specific point, namely at x is 0.10 meters, so which is around here if you do a rough estimation. During this question you have to keep in mind that the produced heat exclusively is transported through the copper tube wall to the ends of the tube, and that the middle of the tube is 20 degrees Celsius because of the heat production. So we now assume for this question that the heat flux is constant. This is very important for the rest of the question, so remember this. And furthermore, you get as a value for the heat transfer coefficient of copper 400, lambda is 400 watts per meter per degree Celsius. So now you can set up the energy balance. The energy balance has to be set up over the small part dx, where the heat is transferring through the surface and heat is produced, which gives the following equation. You have, of course, an energy balance. The E is the heat that flows in minus of at point x, so here, and the heat that flows out at point x plus dx. And of course it's stationary, so it has to be 0. This means that V, the heat flux in, and the heat flux out is the same. So you can say, okay, well, the heat flux overall is the same and it's constant, which is already given. So when you then use Fourier's law, you get the heat flux, heat transfer coefficient, times the temperature difference divided by the distance of the heat is transferring, and this is constant, so we call it C1. If you now use the boundary conditions are of course that if x is 0, then the temperature is 20, and if x is L, or the length of the tube, it's 0. So if we now solve the equation, we get temperature difference, it's minus the constant divided by the heat transfer coefficient of copper. And if we solve this, then you get the x minus C1 divided by x, and of course another constant. And now you use the boundary conditions. So you're gonna fill in these two boundary conditions in this equation to solve the constants. So the second constant has to be 20. If you now fill in the equation for x is L with the value for the second constant, we get C1 times L divided by lambda plus 20, because that's a new constant, is 0. And if we then calculate the first constant, we get 20 lambda divided by L. If you fill in these constants in the equation, we get an overall equation for the temperature of the L is minus 20 divided by L times x plus 20. And if you now fill in the equation at the point x is 0.10, which was the question, then you will find an answer of 12 degrees Celsius. The third question asks you to draw the temperature profile for the copper tube in the sketch by using the temperature equation you had to set up in the previous equation. So from the equation you see that's a linear equation, and you know that at x is 0, the temperature is 20 degrees Celsius, and for x is L, the temperature is 0 degrees Celsius. So, because it's a linear equation, you now only have to draw the temperature profile, which is a linear line. So this is how the temperature profile looks like in the copper tubing if you assume it to be a flat plate. But of course, it is not a flat plate. To get a more realistic temperature profile, we are going to approach the tube as a cylinder. The length of the cylinder is still 0.5 meters and the outer diameter is 2.5 centimeters. I already written it down. And the wall thickness of the tube is, so delta is 2 millimeters. The heat production is 20 watts in the whole tube wall, And to help you solve this problem, you see the sketch of the situation in the left corner. The first question for the cylinder situation was to finish the sketch with all the necessary information, and you see now the answer in the left corner. And the second question was to set up again an energy balance over a small part of the tube, dx, and to solve it and calculate the temperature in degrees Celsius in the middle of the tube. I've already written down the heat transfer coefficient of copper. Okay, we're now going to set up the energy balance of the small part, which is the same as the heat flux in, so at point x, minus the heat flux out, which is at point x plus dx for the small part, and the heat production in the whole tube, so you have to divide the heat production with 2 times the length, because then you have the heat production per meter, and that's what you want, because you have to multiply it by dx, which is the small part you're observing. Of course, the energy balance equals 0 because the situation is stationary. We now fill in the heat fluxes with Fourier's law. A is the surface where the heat flux is transferred through, and that is not a flat plate, but it's now a tube, so we need to observe this surface of the tube because there is the heat flowing through. And we know that the whole tube has a diameter of d, and layer is delta. So the surface is p divided by 4 times the whole area of the circle, d squared, minus the small circle, which is d minus 2 delta squared. And if you write this out, you will find 4 pi divided by 4 d delta minus 4 pi divided by 4 delta squared. And because delta squared is so much smaller than delta times d, we can neglect this one and we will use p delta d. If we now fill in this in the equation, we will find we can solve this equation by using the boundary conditions. And the boundary conditions are, if you think about it, very logical, because the temperature difference at point 0 in the sketch is 0, because the heat production in the middle is exactly the same. The heat is only transferring from the middle of the tube to the end of the tube, and not transferring through the tube, so it has to be 0 there. And we know that at the end, the temperature needs to be 0. If we now solve the equation, we will find an equation with a first constant. But if we use the first boundary condition and we fill in x is 0 and needs to be 0, then we will find for the first constant that it needs to be 0. If we then further integrate the equation, we will find this equation with one more constant. And if we use the second boundary condition, then we find for the second constant that it needs to be this. If we now fill in the constant in the equation we found for the temperature for this tube, then we will find that the overall temperature balance is. And if we now want to know the temperature in the middle of the tube, we only have to fill in the equation for x is 0 and we will find a temperature of 90.9 degrees Celsius. So with a first rough estimation we were not that far from the real temperature in the middle of the tube. The sixth question was asked you to calculate the temperature at specific points, namely at x is 0.10 meter in the tube, and now you will find 16.7 degrees Celsius, and if you will do the same for minus 0.10, you also find 60.7 degrees Celsius, because of course the tube is symmetric. The last question asks you to draw the temperature curve of the symmetric tube in the graph below. Now the temperature profile is as follows. You look to the equation and you see, that's a quadratic equation, so it's not linear, non-linear, and we know that at x is 0 the temperature is 90.9, and that for about x 0.10 and 0. Minus 10, the temperatures are 60.7 and 60.7, so you need it to be a parabolic equation, so you need to get a parabolic graph. And this is about how it looks like. Thank you for watching this video and good luck with the rest of the exercise. And if you have more questions, you can always contact us or the other students via the forum.